Alright, welcome back. MECH1340. We're getting into Chapter 4, Fundamentals of Logic. Alright, basically we're going to be covering AOI logic, ANDs, ORs, inverters, and then carry into that into NANDs, NORs, XORs, those sort of other logic gates that we can use. Alright, so we're using, binary numbers, which we learned in the previous lecture, okay? So binary numbers for all this, if we remember, are highs and lows, ons and offs, trues, false, 1 and 0. So when we've been on the 870 trainer, we're talking about 24 volts and 0 volts when we're taking readings. Okay, if we're on the Adreno, we're using the breadboard companion that we did in digital electronics. Okay, 5 volts on, 0 volts off. So remember, binary is two states. We are on or off essentially, but it can it falls in the category of all these different concepts, right? On, off, open, close, true, false, high, low. And that's the thought process we want to use when we go through doing all of our ladder logic. This and this has to happen, or in how we use that, or not this. All right, and we're going to get into how we imply all those. Okay, so we're going to start talking about when we speak logically, we're going to speak with and or in our vocabulary, and, ors, or nots. Okay, so if we take a look at an example, right, the high beam light can be turned on only when the light switch and the high beam switch are closed, right? The lights need to be on, but the high beam needs to be closed, right? So that's how we're going to turn on the high beam light, okay? The dome light will be turned on whenever the passenger door switch or the driver door switch is activated, right? So like in your car, right? If you have either one of those doors are open, the dome light's going to turn on. If those doors aren't open, the dome light will not turn on unless you manually turn it on. So we'll get into different scenarios like that. But as I mentioned earlier, we call it AOI logic, ands, ors, and inverters. An inverter is a NOT, but it's commonly referred to as AOI logic. But we're going to call them as ands, ors, nots, or nots are the same as inverters. Okay, so the first basic logic gate, okay, this is an AND gate. It's a two-input AND gate. The two inputs are A and B, and the output is Y. So when we refer to A and B, all right, you're going to kind of think of multiplication, but it's not true multiplication, but there's four possible combinations when we do A and B, all right? And we're going to go through all the logic before, so this goes back to our binary numbers, right? 0, 1, or sorry, 0, 0, 0, 1, 1, 0, and 1, 1, right? Those are our counting numbers from 0 to 3, so those four possible states. So when we AND something together, it means they both have to happen for us to get an output. So if we take 0 and 0, our output will be a 0. It's kind of like taking 0 times 0. If you want to think of it that way for simplicity purposes, you can, but it's not 100% just multiplication, okay? Then if we have the other scenario, 0 and 1, we're also going to get a 0. We're going to get, if we have inputs of 1 and 0, we're going to get an output of a 0. And then if we have a 1 and a 1, our output will be a 1. So we use a truth table here, and that's kind of what I just read through. So a truth table tells us all of our possible input combinations and what that output will be. So when we are ANDing, the only true output will be when we have a 1 and a 1. We will get an output of a 1. So for all the others, our output will be false. For 0, 0, 0, 1, and 1, 0, our output's false or 0. When we have 1 and 1, that's the only time we get a true output, which is a 1. So this is an AND gate, all right? So this, this is a 74LS08 chip when we did breadboarding and things like that, so you can look that up, or if you use multisim for this, it's the 74LS08, okay? And we use all the Texas Instruments when we do the breadboarding for those, okay? So this is just going through the truth table here. So I read it kind of through in the last slide, but you can look through it there. It's analyzing all the inputs and how we create that truth table and output. So everybody that's already taken digital electronics with me, this is already reviewed. Those of you that haven't, all right, you can glance and see how the two possible input scenarios produce the possible output scenario. So sometimes you think of and as multiplication, but we're going to start talking about it as scenarios when we start programming. All right, so if we just look at a situation here, right? In order for this light to turn on, we have to have switch A and switch B closed for the light to turn on. Else, the light will not be on. So this switch and this switch has to close for the light to turn on. If only one of those switches is on, okay, or one of those switches is closed, the light will not turn on in this scenario. All right, the next major logic gate is the OR gate. All right, there are multiple AND gates, input AND gates, and multiple input OR gates, but we always start with the basic, and that's why we're using a 2-input OR gate. So A and B are the inputs, Y is the output. That way we can understand what's going on from the most simplistic version. But there are 4-input AND gates and 4-input OR gates and those sort of things. But from our standpoint, we're going to do OR. Now, we write OR as A or B with a plus sign, but that doesn't mean we necessarily are adding, okay? So I want you to take a look into that account. The best way to understand an OR gate is we will always get an output when either one or both of the inputs is a 1 or a high, okay? So if we go through the truth table here, and it's always going to be the same scenario, the same 4 possible combinations we have when we're using a 2-input OR gate. 0, 0, 0, 1, 1, 0, and 1, 1. Okay, so if we have 0 or 0, we will get a 0. If we have a 0 or a 1, we will always get a 1. If we have a 1 or a 0, we will get a 1. And if we have a 1 or a 1, we'll get a 1. So as long as one of the inputs is a 1 with an OR gate, we will always have an output as a 1. So these are a 74LS32 logic gate when we do breadboarding and things like that. Okay, and you can also, just like we did the last one, you can analyze each possible combination here that goes through the truth table and shows when A is 0, when B is 0, when A is 0, B is 1, alright, so on and so forth. You can kind of figure out this piece and how that creates the table for the OR function. Okay, so when we have a real circuit here, in order to turn the light on this way, we can say, alright, if switch A is closed, the light will turn on, or if switch B is closed, the light will turn on, or if switch A and switch B are closed, the light will turn on. So either one of those scenarios will turn the light on. The only way for this light to be off is if switch A and switch B are both open. Alright, so there's the kind of the scenario of an OR. Notice an OR looks more like a branch. I've already kind of mentioned in a previous lecture, if we're going to go in series or in parallel, and how series is more like an AND gate, parallel is more like your OR gate. So if you can kind of think of it, remember when we talked about series circuits, right? It should all make sense. Now if you cut the series circuit, nothing's going to turn on because everything has to work together. Remember, if we had a parallel circuit, alright, since it had multiple paths for current to travel down, if we removed one resistor, it didn't change whether the circuit worked or not. Okay, it just impacted current or power and that sort of thing. Alright, this is called an inverter, sometimes called the NOT function. So what you're doing is you're taking whatever that input signal is and you're switching it out or flipping it to become the opposite. Okay, so if it was low, it becomes high. If it's high, it becomes low. So when we send in a 0, we get out a 1. If we send in a 1, we get out a 0. So it inverts the signal. Okay, it's called the NOT function. And we notice at the top, it really is symbolized with a bar. So you can say a bar, or as it has in parentheses, you can say not a. Either one is acceptable. So you can say a bar or not a, and it means the exact same thing. We're using an inverter. So this is a 74LS04 chip when we do breadboarding and things like that. Okay, so this is the NOT function. The AND, the OR, and the inverter, the NOT gate, are all the fundamental logic gates for what we use. Now, a lot of the logic gates that we use in like your phones and computers and things like that, those are all used from NAND and NOR gates. We'll get into those a little bit later on. But these are the foundation and the fundamental logic gates that you use so that you can start understanding thinking logically to be able to program things logically. Okay, so this would be symbolized with a closed contactor. So one thing that you really need to know, all right, whenever we do the inverter, anytime there's a circle on any electronic component, it means that we are inverting that. So you're going to see a NAND gate that looks like an AND gate with a bubble on it. That becomes a not AND. Or a NOR gate. We would take an OR gate, put a bubble on it, okay, and it would make it a NOR gate. So that bubble is very significant, all right? Now, when you get into D flip-flops and things like that, the bubble means something, all right, whether we're inverting the signals or not. So anytime you see that little bubble, we're inverting the signal. Okay, so let's take a look at this scenario here. We got a normally closed push button. So what really happens here, right? As of right now, that circuit would turn on because the push button is wired normally closed, and it only opens, right, when you push it down. So we can use a push button as a not function. Alright, so if it's normally closed, if it's not normally closed, the light will not be on. So we can flip that signal. So if it's not pressed, the light's on. If it's pressed, the light's off. Just an example of how we can invert a signal. It's not the only inverter type scenario, but it's just kind of designed for you to understand. Okay, we also use the not function with other gates. So I can invert a signal before I send it into an AND gate. So in this case, I'm going to send in, A and B, and what I get out is A and not B, or A, B bar. That would be my output algebraically, or my output on this case would be produce a high, a 1, because we've inverted the B signal. Okay? If we send in a 1 and a 1, all right, and B is inverted, then we get a 1 and a 0, which becomes a 0 in this case. So we can use the not function with AND gates, we can use it with OR gates. Okay, and I talked about this one before. This is a NAND gate. All right, it means not AND. So when you do this, it's the exact opposite of a NAND gate. Remember, the output truth table for an AND gate was 0, 0, 0, 1. The output for a NAND gate is 1, 1, 1, 0. It's the exact opposite. Why? Because we're inverting the signal after we AND it. So here's how it kind of looks, all right? The NAND gate looks just like an AND gate. We got that bubble on it, though, so we're inverting it. So it's pronounced a NAND gate. And a lot of the technology that you use all uses a NAND gate, because we can actually make any kind of chip we want using a NAND gate or a NOR gate. I can turn it into an AND function. I can turn it into an OR function. All right, I'll go over more of that in class on the board and kind of show you that. Some of you guys remember doing that in digital electronics. We had to take the date of birth project and turn it all into NAND technology. But if we go through this gate, I have A and B, so 0 and 0, and then I invert it and I get a 1, because 0 and 0 is 0, and then I invert that 0, it becomes a 1. If I have 0 and 1, that's a 0, and then it gets inverted with the bubble, right, and then becomes a 1. If I have 1 and 0, that creates a 0, and then I invert it and creates a 1. Then I have 1 and 1, which is 1, and then I invert it with the bubble, it becomes a 0. So that's how your NAND gate works. And you need to know all the truth tables for all of these. So for the NAND, the NOR, the AND, the OR, the inverter, the XOR, all these that we're going to get through. Okay, this is a NOR gate. Okay, so it's the same kind of concept as the NAND gate. We're going to take an OR gate and invert it. So we call it a NOR, which means not OR. So it is the exact opposite of an OR gate truth table. Okay, so in this case, if I have 0 or 0, that produces a 0, but then I invert it because it's a NOR gate, which gives me a 1. If I have 0 or 1, that produces a 1, and then the bubble on the NOR gate inverts that, which creates a 0. If I have 1 or 0, okay, that's normally a 1. The bubble on this inverts it, creates a 0. And then when I have 1 or 1, I get a 1, and then the bubble inverts it, creates a 0. So that's why the truth table is the exact opposite of the OR gate. Okay? And so picture down here, I didn't talk about on the left side, but that's the logic chip that we would breadboard. So those are 2 input NOR gates, All right, and then remember pin 7 goes to ground, pin 14 goes to VCC. So we can hold up to 4 gates on one chip, and that's assuming that these are 2 input NOR gates. Okay, the exclusive OR. Okay, very, very important chip for us. We use this for a lot of comparators, latch memory, things like that, adders. This is where they all come into play here. All right, so we use these kind of chips more to latch in memory and that sort of thing. So when we use an XOR, and this is normally symbolized as an A plus B with a circle around the plus sign. So that's even on the Siemens test. So make sure that you know that. That's going to look like A plus with a circle around it B. That means A exclusively ORed with B. What does that mean? That means as long as one of the inputs is high, one of them has a 1, we will output a 1. If they are both 1, we will output a 0. If they're both 0, we output a 0. So the exclusive OR means we are only exclusively ORing A and B. So only works, we only get a high output if one of the inputs is a 1, not if both, and not if they're both 0. Okay, so it's a comparator for us when we go through those sort of things. So this is the exclusive OR chip. Okay. Now, many of you guys in digital electronics hated Boolean algebra, but it's really just your basic algebra and simplification. All right, so we were able to take this big old expression here, right? So basic logic circuit here, where we have A and not B ANDed with not C, all right, and then we invert that whole signal, right? We had to use De Morgan's theorem, break the line, change the sign, that sort of thing. So not everybody's gone through this, but we'll get through a little bit. I'm going to do some more examples on the board in classes as well. But I want you to be able to actually write, okay, the min term or the logic expression for y, being able to go through these gates here, okay? And then how they relate to, you know, our ladder logic. An OR gate. So our graphic symbol, right, would be 2 normally open contactors branched together, which means OR. Then if the next one, we have an OR with a NOT. So a NOT is the normally closed contactor there. Okay, and then when we have an AND, they're in series. So if you remember that OR is in parallel, and a basic OR has 2 open contactors. If you remember that a NOT gate means it's a contactor with a line through it, means normally closed contactor. All right, that'll help you understand the NOT gate. And so just remember, ANDs are in series, ORs are in parallel, and then NOT gates have the line through them. Very simple for us to take a logic expression and turn it into ladder logic and write it. Okay, so how do we understand how to write these? Okay, so when we write an AND, okay, we have our 2 inputs, A and B, and our output's a Y. Okay, so when we rewrite that, we're going to say Y equals AB. We're kind of emphasizing mathematically that we are doing some sort of multiplication. So an AND gate, our output is Y, our 2 inputs are A and B, so we would write it as Y equals AB. Or you would say Y equals A and B. Okay? If we look at the OR gate, we have 2 inputs. The inputs are A and B. The output is Y. We would say Y equals A plus B, but we don't like to say plus, but that's how we show what an OR gate is. But we say Y equals A or B, and we are saying that if you see a plus sign, it means the word OR. So that's why we say Y equals A or B. We do not say Y equals A plus B, because that's not mathematically correct for us either. And then when we have an inverter, right, like the bottom one, we would say Y equals A bar or Y equals A naught. Either one of those terminologies is acceptable. So understand, when we write out the Boolean expression for this, when it's an AND gate, we show like they're being multiplied. When it's an OR gate, we show like they're being added. And when it's inverted, we put a bar over the top of it. Okay, so that's really what that means. Okay, so logically, if we have A and B, right, it would be outputted as AB. If we use a NAND gate, right, it's A and B not, with the not being the bar over AB. So there's how we would write a NAND expression. Okay, and then if we have an OR, right, OR is written as A plus B, really correctly saying that as A or B. And then the NOR is just like the OR with a bar over it because it's not OR. So you'd have A or B not. And the bar would go over the whole expression. Whatever comes out of that gate, the bar goes across everything with that inversion bubble. Alright, so let's learn how we can do some combination logic. So that's what this is called, combo logic, in order to produce an output. So we always go left to right, top to bottom, and you always write what goes out of the gate next to it so it helps you understand it. So we have A and B, that A and B going into the OR gate, or to the AND gate. So we rewrite the output of that AND gate as AB, and then that AB is going into an OR gate, and so is C. C is also going into the OR gate. So our final expression or equation would be y equals AB or C, right? You write it as AB plus C, but you say it as AB or C when you go through that. Okay, let's take a look at the second example. We have A and B going into a NAND gate, and then C is following that up into the OR gate. So we have A NAND B, so that would be AB bar, and then OR C, so y equals AB bar or C, or not AB or C, however you want to say that one. I like to use bar when it has a whole bunch of variables incorporated in it. Okay, so ideally you want to write the output after each logic gate. So let's look at the third one. We have A or B, so we write the output there as A plus B, and then that's ANDed with C. So notice how we have to put A or B in parentheses. We put A or B in parentheses, and then it's multiplied by that C at the end, showing that it ANDs. And from algebra, you can actually distribute that. So that can become AC or BC. You can distribute that C through the expression if you need to. Okay, and then let's look at the last example. We have a NOR gate, which means not or. So we can say A or B not. So the bar would go over the A or B. And then that's ANDed with C. So notice that we have A or B not, and then C is going on the outside of the parentheses, like multiplication. Now, since there is a bar over the A or B, you cannot distribute the C through using Boolean algebra. But in the third example, you can distribute through, but not in the bottom one. All right, and here's kind of the laws that hold true. These are just your basic algebra laws. Okay, so you can write these down and understand them. I'm just going to kind of, maybe pause the slide and write them. You should know these now from algebra, whether we have commutative law of addition or commutative law of multiplication. Same with associative law and the distributive law. And you use those three basic laws to simplify using Boolean algebra. And essentially when we do Boolean algebra, we're either going to, do a lot of factoring or some distribution as we go through those. Okay. But our main focus isn't to do a ton of Boolean algebra in here. We really want to develop, logic gate circuits from Boolean expressions when we do this. Okay, so we've already done this example, right? We have y equals AB or C. So we use an AND gate for the AB, and it's got to go into the OR gate, and it gets ORed with C. So now we're going the other direction. Okay, I'm going to give you the expression y equals AB or C, and I expect you to be able to draw the logic gate down below that applies to that expression. So anytime things are multiplying together, we need an AND gate. Anytime we see things adding together, you need an OR gate. So we're going backwards from before. So the examples a few slides ago, right? I gave you the logic circuits, and you had to come up with the expressions for the outputs. Now I'm giving you the expression, you have to come up with the circuit for it. Okay, so if we take a look and I give you this expression, y equals A, quantity B, C, or D, all right, I need to know that B and C are getting ANDed, all right, and then that's getting ORed with D, and then that's getting ANDed with A. So when we're going this direction, we work our way inside out, inside the parentheses to outside the parentheses last. So notice we have B and C going into an AND gate, then that's getting ORed with the D, and then lastly that's getting ANDed with the A. So we're going to work our way inside out as we create the logic circuit for this. Alright, so now we got to go from a Boolean equation that we're going to create here. So now we have the logics, gates, okay, that are given, and we're going to create the Boolean expression. So we can see that A and B go through an OR gate, and those get ANDed with C, and they also get ANDed with not D. So everything that's ANDed is multiplied, and everything that's ORed is plus. So down below, the answer for this expression is y equals C and not D, parentheses, which is also ANDing A or B. So that's the correct way we would write the output expression for this logic gate. Okay, you should be able to follow these through. I'm not going to read through all this one because it gets kind of confusing if I just keep saying letters as I'm going through this. But you should be able to trace those inputs, A and B, and notice that you write the output out the outside of each gate. That will really help you get down to the final expression. So this one you should be able to kind of go through your own, taking a look at this this circuit and coming out with y equals A bar B or A B bar. That actually produces a special gate. That actually produces an exclusive OR gate. Okay, so all of these, so there's what? 1, 2 inverters, 2 AND gates, and 1 OR gate actually produce an exclusive OR. So we wouldn't need to do this entire circuit. We could just use an exclusive OR gate and send A and B into the exclusive OR and get the exact same expression out of that, saving us the cost of buying 3 different chips when we can do it with 1 chip. Okay, so simplified version there. All right, so if we talk about hardwired, okay, versus programmed. So in this scenario here, this is more of our ladder logic. Okay, so what's the difference here when we have hardwired logic versus programmed logic? So when I want you to think of, when we talk about hardwired logic, that's relay logic. So out in the field, you open up a control box and you see all these relays that are wired in there. That's called hardwired. Okay, so for us to rewire something or rechange some of the controls, we have to physically go out there and rewire all the connections up that we need to. Say we accidentally needed to OR something and we ANDed it. We'd have to physically go out and rewire all that. Whereas when we're using our control program, everything's wired to the I/O on the PLC. So if I accidentally did that ANDing and I needed to OR something, I just changed the program real quick and we're done. So that's kind of the difference. Hardwired, a lot more work, and you physically need to go take care of it, versus controlled. Everything's already wired to specific I/O. We just change the program real quick and re-upload it to the PLC. Okay? So everything that we do here in the PLC is pretty much, used to or using our logic that we've learned. If we notice here, all right, so what's the gut of the ladder logic? That's the stuff in the middle where it says rung 1, rung 2, rung 3. Okay, the stuff out there, okay, we have is kind of representing how we're getting wired into the PLC. So that input module, that's not in your ladder logic program. That's your PLC input. We have the stop button, okay, that's normally wired closed there. The start button, it's normally wired open. Then our overload relay is normally closed contactor for your motor starter. Then we have the output module, which is the motor coil. We have the green and red lights that are indicating, if it's on or off. And so those aren't part of the ladder logic. That's how it's hardwired in the field. We're going from the power, okay, to the specific button to the input module, okay? Same with on the other side, the output module, the PLC, and then it's going what? To the specific device and then to power. All right, so in between here is all the control logic and the programming that you're doing. What I want you to think about though is if we look, and I'm going to look at rung 1, what's ANDed there? The stop, the start, and the overload relay contactor and the motor coil. Those are all ANDed. Okay, and then we have another motor contactor that's ORed with the start button. We're going to learn later on that means, okay, that's our seal-in logic. So when I hit the start button, I don't have to hold the start button. It'll automatically close itself and stay running until the stop button is hit. Okay, that's seal-in logic. I want you to think about that for later on. Okay, and then if we look at rung 2, it's normally closed. That's our motor contactor. So what's going to happen is, as long as the motor's running there, right? Okay, the green light's going to be going. If something changes and that opens, the green light will turn off and the red light will turn on. So just think about those different scenarios there. Okay, and here's what it would look like. And once again, this is Allen Bradley, so our software is going to look different with all the Siemens PLCs we're using the Step 7 through TIA portal. Okay, but similar ladder logic, but like I said, it's going to look slightly different on our screen, but this is using the Allen Bradley Logic Pro stuff. Okay, so if we take a look at PLC language and our ladder logic, each one of those contactors, those are our instructions. So shown here, the 2 instructions on the left, those are normally open contactors. Okay, on the right, okay, that's our coil, usually turning on our motor or light or something like that. Those are our outputs. Okay, so we have input instructions and output instructions. We have our rungs, and then we have our rails. Okay, so a ladder logic program can consist of many rungs. All right, you can keep going, and each rung has to have either some sort of input conditions and output conditions on each one. Okay, so if we take a look at the relationship between schematic to ladder program logic. So if we look at something schematically on the left, okay, we can see that there's limit switch 1, limit switch 2, and a solenoid. Okay, so that would mean what? Limit switch 1 and limit switch 2 have to be closed for the solenoid to turn on. That's really what that means. In ladder logic, it would be what you see on the right, where we have normally open A, normally open B, and our coil for Y. So notice, since limit switch 1 and limit switch 2 are both normally open symbols, all right, our contactors for A and B are normally open. Okay, and then we would use a logic gate for that. Okay, so there's how our logic relates to our ladder logic as well. So remember, ands are in series. Okay, same kind of concept here, and there's what it would look like on our Allen Bradley software. Okay, limit switch 1, limit switch 2, and our solenoid. Okay, notice the addressing tags, those are going to be different for us in Siemens as well. So Siemens, we might have like I0.1 and I0.2, and we might have Q4.0. So just some subtle differences there. Okay, now this is if we are ORing. So schematically, if we have limit switch 1 or limit switch 2 can turn on the solenoid. So A or B can turn on the solenoid. So both of those are normally open limit switches. So A and B are shown as normally open contactors in our ladder logic program. Okay, and the solenoid is still shown as an output. So we should see, right, we have our Boolean equation, our logic gate for an OR. So A or B turns on Y. So remember, ORs are in parallel, ANDs are in series when you think logically. So in our ladder logic program, we would write this as limit switch 1 or limit switch 2 will turn on the solenoid. Alright, so we can use them together now. So I want you to think about this. We're taking our ANDs and our ORs and putting them together. So we have limit switch 1 or limit switch 2. Either one of those can turn it on, but we need to AND that with a pressure switch. Alright, so it can be limit switch 1 and the pressure switch turns on like the light, or limit switch 2 and the pressure switch turns on the light. Okay? That's really what it's coming down to. So we can see now how our schematic creates our logic gate diagram, which can create our ladder logic program. So we can see where we have A or B and C and how that relates to our output. So hopefully we're starting to put all this together. I know those of you guys that took digital electronics, this is hopefully making a lot more sense to you. Those of you that didn't take a digital electronics, all right, hopefully this is coming together for you, so you can see how all three relate to one another here. Okay, and then obviously you should be able to kind of figure out how the program works here. The program looks, pretty identical to our schematic, and even, kind of how our logic gate is going through. Okay, then as we add more, okay, so in this case we have what? A or B ANDed with C or D. So you have to look at all the possible combinations we got here and how this creates our ladder logic program. So if we look, right, we have A or B. Okay, so it has to go through A or B, and then it has to AND with C or D. So there's multiple ways to turn on this program here. Okay, so just think about how these relate. So, you know, pause this, take a look at it for a little while, and you guys can kind of see, all right, how each one of these works here. Okay, so we have limit switches, flow switches, that turns on the pilot light. And you can see how those different paths can work in order to turn the light on here. Okay, and there's how it's going to relay in your program. Like I said, we're going to get into programming real soon here if we haven't already started by right now. Just, you know, implementing some of the basics and understanding how to write this in TIA portal. Alright, so if we have, you know, the limit switches have to be, we have 2 in series and 1 in parallel. You guys can see now, I think you're getting the gist of this. I'm not going to dwell on these too long, but you can see where we're ANDing, where we're ORing, and how we get that output. Okay? Same thing here. You know, just pause these and take a look at it. But we have A and B or C and D will create our output. So I think we can really kind of see here how everything is coming together, and we can create and go from our schematic to our logic gates, and then take our logic gates and create our ladder program. Okay? Same thing here. Just a combination of the, you know, seeing the same things and seeing it in the Allen Bradley program here. Here's one that's a little bit different, right? Because what's going on differently here? We have limit switch 1, and then we have push button 1. Notice on the schematic that the push button is wired normally closed. Since it's normally closed, we have to use the not B. So we're going to use the normally closed contactor. So logically, as long if the button's closed, the push button's closed, we have to use the inverter. So it's not B and the limit switch A. Okay, so not B and A, and we would have to make our ladder logic match that. Okay, and then here's what it would look like. Now notice it's a little bit different here with how Allen Bradley does it. In Siemens, we will have normally closed contactors on the program here. Okay, so now we can see this schematic, right? We have A and not B, or not A and B. This is what I was telling you about earlier. This is an exclusive OR. An exclusive OR. So if you look down below at the bottom of this slide where it says Boolean equation is not A and B or A and not B, notice there's that plus with a circle around it. A exclusively ORed with B. There is a specific chip here, right, the OR gate with the extra bar behind it, that creates this circuit. I mentioned this earlier in the lecture as well, but I want you to know that Siemens does have a question on their test. I've seen it a few times where they have what, you know, logic gate does the A with the plus sign circle around a B equal. It looks just like what you see at the bottom of the screen there, and the answer would be the exclusive OR, the XOR circuit. So make sure that you guys take note of that. Okay, and here's what it would look like on your ladder logic program for Allen Bradley. Okay, now we can look at all these other ones. I think you guys can, you know, figure this out, how we're ANDing things and how we're ORing things. You know, you can take a, you know, pause the video and take a look at these different things here as you go through it. Okay, so if we want to get to word level logic instructions, okay, this is how you and I need to be able to speak when we're talking logically. Okay, so understanding how we use AND. So there's different parts of scenarios that we're going to get through. So what I want you to know is if we're matching, okay, when two things are on, we need to AND something. Okay? If two different words are on, we can OR something. Okay, when one or the other has to be matching, that's when we use the exclusive or. If we want to reverse the state or invert it, we're going to use the word not when we go through this. Okay, so if we look at what happens here, this instruction right here, okay, we're going to have the processor perform an AND operation on B35 and B37. So you can see that up above, okay? So we have A and B, and then it's going to store the result in B310. So you can go through, right? When you have 1 and 1, you get a 1. 1 and 1 is a 1. When you have 0 and 1, you get a 0. 0 and 1 gets a 0. You guys can see that, right? We're just going straight up and down in the vertical connections there between A and B. And we're just completing what's in that destination there. So we're just comparing, or we're essentially ANDing through all those. Okay? And we can look at the tables, and we'll do that in the Siemens software as well. This is where we can OR. Okay? So we're going to OR 3.1 with 3.2, and we put it into our destination 320. So we can actually do some Boolean, within our ladder logic as well. So we can see that 1 or 1 gives us a 1, or 0 or 1 produces a 1. 0 or 0 produces a 0. So we can do all that operation and store it in the destination as well. When we're comparing bits, we can actually take a look at each bit, okay? And we'll pull up the binary tables and look through the functions as they go, okay? We can do the same thing with an XOR. Remember, an XOR outputs a 1 only if A is a 1 or B is a 1, but not when both are a 1, okay? So we can control where things work and where things don't work just by, using our basic word level instructions of our logic gates when we go through this. All right, and then we can just take a look here. Here's what it looks like on the table using the XOR using our Allen Bradley stuff. Okay. Same thing with a NOT. Notice, remember, a NOT just inverts the signal. So if it's a 0, it becomes a 1. If it's a 1, it becomes a 0. And we can output that entire word and store it into a specific destination. We're really just storing bits. We're keeping track of things in memory here, essentially what we're doing. Here's what it looks like in our Allen Bradley software. And like I said, ours is going to look a little bit differently, and we're going to get heavy into this using our Siemens TIA portal. But it's a good idea for you to kind of see what's going on. So what have we learned in this chapter? We learned about ANDs, ORs, inverters, NANDs, NORs, and exclusive ORs. We learned what those logic gates look like and how we implement those logic gates. And then how we can actually create a Boolean expression from those logic gates, and how those logic gates actually translate to our ladder logic, and understanding that ANDs are series, ORs are parallel, and we can do combination logic of creating ANDs and ORs and inverters and all those different things to create our scenarios. So what I want you to think from now, when I start giving you, programs to write, I need you to start thinking of this and not this, or this and this to make this turn on, or this needs to happen for this to turn on. I need you to start using ands, ors, and nots in your vocabulary. That will really help you understand and translate that into ladder logic. Okay? Alright guys, that's the end of this lecture. Like I said, email me if you got any questions. Else guys, I'll see you in class. Have a great day.